Positioning sampling units in the landscape. How do we decide where to put our sampling units when we are determining our sampling design? These decisions are made with respect to the need for good interspersion throughout the population or the area of interest, practical constraints of time and cost, and the need for randomization. There are various approaches to locating sampling units that exist, and we're going to review a few of them now. One of the most commonly used approaches is simple random sampling. With simple random sampling, each sampling unit has an equal probability of selection, and the selection of sampling units is independent. So there is no relationship. If one unit is selected, it does not impact whether another unit is selected. Simple random sampling is best done in relatively small, relatively homogeneous areas, especially if the required sample size is not overly large. The advantages of this approach are that the data are easy to analyze and it meets assumptions of independence. Disadvantages are that just by chance you could have poor dispersion of units, and potentially it could be very inefficient if you're dealing with a relatively large area. There are a couple approaches to randomly allocating or locating units. The first one is the coordinate method. In this case, we have our area of interest, and we superimpose an XY coordinate system over the general area of interest. We then select XY coordinates randomly and then examine where they fall. If the XY coordinate falls within the area, we would keep it, and if it falls outside of the area, we would reject it. One of the disadvantages of the coordinate method, especially if we're using transects, is it's possible to locate an XY coordinate that exists in the area, but that would put the transect outside of the area of interest. If we reject those points, we have effectively reduced or shrunk the area that we're studying to accommodate those lost units. One possible solution that may be used is if a XY coordinate puts a transect that it would go outside of the unit of the area of interest, you would then bend it back at an angle so that you would sample in this area out here. Another approach is the grid cell method. In this case, we overlay the area with a virtual grid, and the grid cell size and shape is equal to the size and shape of the sampling units, so that the possible number of sampling units are displayed in this grid. We randomly select grid cells without replacement. And essentially what this does is allows us to use randomization and independence to locate our sampling units. Now you can see by comparing these three different possible samples that we have variation in dispersion, and we can get, this is one of the disadvantages, we can get under dispersion where some areas are overrepresented and other areas are underrepresented. An alternative type of sampling is restricted random sampling, and this is best applied when the number of samples must be relatively low. In this case, we want good interspersion of units, and so what we do is we divide the area into segments, and then within a segment we randomly locate one sampling unit. In another segment we randomly locate another sampling unit. If we have the same number of segments that we have required sampling units, we then end up with one sampling unit per segment. The advantage of this is we get relatively good interspersion, although occasionally you may run into a situation like this where two sampling units are relatively close to each other. Stratified random sampling is very commonly used in natural resource measurements. In this case, we stratify an area into subtypes that are based on some kind of classifying characteristic. Oftentimes this can be vegetation type, soil type, ecological sites, landforms, anything that is not the attribute of interest. We allocate sampling units to the different strata. And the advantages of this are that it's very efficient. We can get an improved quality of information for the different strata in a variable environment, and the data from each of the stratum may be analyzed either separately or together. Now there are different approaches to allocating units to the strata, and we will examine two of those now. Proportional allocation is where we allocate units to the strata based on it's proportional to the relative area of each strata relative to the area of the entire population or area of interest. For example, if we need a total sample size of 20 and the loamy uplands is 50% of the total area, we would allocate 10 units to loamy upland. Granite Hills is 20%, it would get 4 units, and the draw would get 6, representing 30% of the total number of sampling units. Optimum allocation is an alternative approach that aims to give the best information for a given level of sampling effort. The allocation of units to the strata is weighted by variability of each strata. So we have to have some information about the variability of each strata. Let's take an example and assume that we've done some pilot sampling that's indicated that the Granite Hills ecological site has the highest variability of the 3 ecological sites. It also has the smallest relative area at only 20%. And if you recall from the proportional allocation, we would have put 4 units, sampling units, in the Granite Hills site. So based on our pilot sampling, we already know the proportion of the areas, and we are able to determine some measure of variability, the standard deviation in this case, for the different sites. And we can see that loamy upland has less variability than the Granite Hills. We then calculate, we multiply the proportion of the area by the standard deviation. That gives us a value that we then sum for the area, and then we take this proportion, this weighted proportion, and divide that by the sum for the area to come up with a weighted ratio. We then multiply that by the number of sampling units that we're going to put in the area, and what this gives us now is a new allocation of sampling units to the different strata that's weighted by both the proportional area and the variability of these areas. In this case, the loamy upland, which formerly had 10, would be reduced to 5, and the Granite Hills, which formerly had 4, would be increased to 11. Because the Gravelly Hills area is more variable, it would take more sampling units to estimate the variability as well as for the other strata. Systematic sampling is commonly used as well. This involves regular placement of sampling units. We divide the area into equal segments, randomly locate the first unit, and then systematically place others at equal distances subsequently. In another approach, we can use a combination sampling unit that is a transect. We then randomly locate the first quadrat, and the subsequent quadrats on this transect are located systematically from that first quadrat. We do the same with the next transect, locating a new starting point for the quadrats that are then systematically placed after that first one. And we do this repeatedly until we have all of our sampling units allocated. The advantages of systematic sampling is that it does give good dispersion, and it can be far more efficient than random sampling. Potential disadvantages are that we can under or overestimate the attribute of the variable of interest if there are some regular patterns in the vegetation, and because these are not randomly located, there is the potential for bias. Selective sampling is another approach that we can use. This is sometimes called subjective sampling. In this case, sampling is restricted to key areas or critical areas. The focus is on providing information that's driven by management issues, and so if we know that we want to sample specifically in targeted areas, we use selective sampling. Because the selection of locations is non-random, it does have a potential for bias that must always be considered. Cluster sampling is another approach. In this case, we're measuring small-scale variation within a cluster of individuals. This is best to do when it's difficult to take a random sample of the element of interest. Let's see how this works. We randomly locate a belt transect, and then we measure the element of interest on every individual that occurs within that belt transect. Again, we have another belt transect, and we measure every individual that occurs within that transect. Double sampling is an efficient approach to estimate a variable when it is a costly or difficult to measure. It incorporates frequent estimation and infrequent measurement. Double sampling is commonly used for production estimates. So in this example, what we have is 4 quadrats. We have estimated production in 3 of them, so that's the frequent estimation, and in the 4th one we estimate and then we clip or harvest all of the vegetation out of that quadrat. That's the infrequent measurement. We then repeat this process of frequent estimation and infrequent measurement. So now what we have is 12 quadrats that we have estimated, and of those, 3 of them have been estimated and measured. The estimated variable correlates with the measured variable, and if you have a good relationship between those two, you can use that information to estimate the attribute of interest. So whether we need good dispersion through the population of interest, we have to consider the practical constraints of time and cost and the need for randomization, all included with our management and sampling objectives. These are the criteria that we use in order to determine how to position our sampling units in the landscape.